So when we're using vibrational, it's vibrating in a particular location. So for a solid, we'd see particles, and they would just sort of wiggle in place. Back and forth and back and forth, up and down, wiggle in place. Rotational turns about an axis. And translational is freely moving from place to place. So hopefully that will help you get a mental picture of what we're talking about, each one of these kinds of energy. So when we talk about an object having kinetic energy, where does the kinetic energy come from? It comes from all of those. So internal kinetic energy is due to the motion of the particles. Kinetic energy, like we did in Physics 1, is about the movement of the whole object. Luke runs out into the hallway. He has kinetic energy. But we're talking about now gasoline in your car engine. Gasoline has kinetic energy internally because of the motion of the particles. So what we're doing when we burn it is we're taking some of that energy out and using it for whatever we want to use it for. Now, that's our internal structure piece. And the other thing we want to keep in mind here is that how do we measure this? Because clearly Andrew can't go and grab all the little molecules and measure their kinetic energy. Because if he grabs them, they stop. So how do we possibly measure this internal kinetic energy? Well, we measure it indirectly. Using temperature. So temperature is a multiple of internal kinetic energy. Temperature is some number times our internal energy. So if water has an internal energy of 3 joules, then temperature is a multiple of that 3 joules of energy. So something that is hotter would have more energy, and something that's cooler would have less energy. So when we think of cold things, what are some things you think of when they're cold? What's a cold thing? Ice, which is solid water, right? The particles have stopped translating and not completely stopped rotating, but basically completely stopped rotating. They're just now sitting and vibrating. Cold things have low temperatures because you have a small amount of kinetic energy. You've lost energy. Gases would have high kinetic energy in general because they're able to not just vibrate, but also rotate and move from place to place. So that indicate a higher temperature. Yeah?
What about like liquid nitrogen?
So some materials, that temperature is relative, right? Like liquid nitrogen does not stay liquid for very long. It is a super cooled liquid to get it into a liquid state. So like for air and water, the temperature to become a gas is pretty low. For liquid nitrogen, it's really, really, really low because it typically exists as a gas in nature. So to remove energy from it, you're removing energy till you get it cold enough that it will change from gas to liquid. So it's kind of one of those how big is it? When we say something like, how big is that? Well, it depends on what you're talking about. Because if I want to say, how big is an airplane, comparing it to crackers is probably, that's about 11 million crackers. Well, that doesn't make any sense to me, right?
Do you think you could like cool liquid nitrogen enough where it's like a solid?
They can. It requires a lot of energy to do that. And so it's not very cost effective. So they don't typically. But yes, we have gotten very, very close to what's called absolute zero, and that's what I'm fixing to talk about here in just a second. And but it does cost a lot of money to remove the heat. And the lower you get, the more heat you have to fight to get it out. So we'll talk about that here in just a second. So we have 3 temperature scales. We have Fahrenheit. This is the British Imperial. And what is freezing point? What is the freezing temperature? Like we say below freezing when it gets cold. What's the number for that? 32 degrees Fahrenheit. Do you know what the boiling point is for water? It is 212. For freezing, and this one is for boiling. Celsius is the typical metric scale. So what's the freezing and boiling here? 0 degrees and 100 degrees. And that's a forced one. All scales are forced because where did Fahrenheit come from? Well, it was kind of like they used salt water, and how low did the temperature have to be to freeze the salt water? It's kind of like, what's the lowest temperature you can get in your lab? Let's call that 0. What's the highest temperature you get before the water boils off? Turned out to be 212 when he started counting how he was measuring it. That's why we have weird numbers for Fahrenheit. Because salt water takes longer takes a colder temperature to freeze than regular pure water. So the ocean doesn't freeze as easily as like a lake would. That's part of it. And then just the sheer mass of water is another one. So, but the one we're going to use a lot, we'll use Celsius a lot, but we will also use the Kelvin scale. And Kelvin, water freezes at 373 and boils at, 273 and boils at 373. And it has this cool one, 0 Kelvin is called absolute 0. And you've probably heard that term, right? Everybody heard the absolute 0 term? The Kelvin measurement was intended to say this is the moment in which you lose all your internal kinetic energy. If we're going to make a scale that's based on kinetic energy, 0 should be at 0. So 0 Kelvin should be no kinetic energy. And then they just divided up the numbers so that the 1 Kelvin would be equal to 1 degree Celsius. So in other words, if Luke needs to do something and the change in temperature is 53 degrees Celsius, it's also 53 Kelvin. But the two numbers for the temperature will be different. The temperature in Celsius might be 290, and in Kelvin, temperature in Celsius might be 90 degrees, and the temperature in Kelvin might be 63 degrees. you get different numbers. But in Kelvin, you don't say degrees. And it's really hard for me because I don't use it a lot, right? Like your everyday life, you don't use Kelvin. So when you talk about Kelvin, it's not degrees Kelvin. It's literally just 5 Kelvin, 273 Kelvin, where the other two are degrees Celsius or degrees Fahrenheit. What were you going to say? Nothing? Okay. It's all good. So when you freeze things, you typically are removing, first of all, when you go from gas to liquid, you've basically removed all the translational energy. When you go from liquid to solid, you've now removed almost all of the translational and rotational. And if you get to absolute zero, you have no motion of any kind. We've never done that. And one of the laws of Thermo says we're not capable of doing that. Just like you can't go the speed of light. Because anytime you try to measure the speed of light, it's still going to be the same number. Even if you're going near the speed of light, it will still look like light is going the speed of light. Because it's weird like that. We'll talk about that later. Because we get to do some of that in this class. Some of those weird things that happen. But the other one is, if we can't get fast enough to go the speed of light, we also can't get cold enough to get to absolute zero. The closest we've gotten, I want to say, is 99 point, and there's 4 or 5, maybe 6 decimal nines. So 99.9999, or one more percent of the speed of the temperature Kelvin, 0 Kelvin. Here's why. What happens if you put a hot thing near a cold thing? The cold thing gets hotter and the hot thing gets colder. Do you ever have it happen where you like take a soda out of the fridge and put it on the tabletop and the soda keeps getting colder and colder and the tabletop gets hotter and hotter? Like hot flows into hot and cold flows into cold? Yeah, it doesn't. So when we try to get something to absolute zero, guess what happens? We have other things around it that are not at absolute zero. And so we call this thermal contact. And since things are in thermal contact and they exchange energies, we're having trouble with that 0 Kelvin. The other thing is we're not sure if it might do something really bad. JD, is it Salinger? Yeah, Salinger. No, Farragut. Kurt Farragut wrote a book called Ice 9. And the whole plot of Ice 9 is that this guy was trying to create fake ice to do things. And his 9th version of it was able to get to absolute zero. But as soon as it got in thermal contact with everything else, those things froze. It was like a black hole of heat energy. And so if it ever loses control of it, then it'll kill everybody on Earth. Everybody will freeze. So it's kind of a story about how we're going to protect this from getting out so that everybody doesn't die. And Kurt Farragut being Farragut, or Vonnegut, not Farragut, it's Vonnegut, Kurt Vonnegut. Good gracious, my brain is rotten. I'm telling you. Vonnegut. He writes very sad stories, so he had a very cynical view of life. Life sucks, then you die. That was kind of his mojo. So don't anticipate the book being fun to finish, because it wasn't. All right, so Kurt Vonnegut. Now, thermal contact. Does not require physical contact. It occurs when objects can exchange heat energy. So do we have to be touching the campfire to get heat from the campfire? No, mercifully. What about the fire at our fireplace? We don't have to touch the fire to feel the heat energy from the fire, right? Just like if you open the fridge, sometimes opening the fridge gives you a nice cool breeze. Feels good. You've been outside on a hot day, open that fridge up, feel that cold air. Good thing. That's thermal contact. So when we talk about thermal contact, it doesn't have to be physical contact, although you could. My dad told me one time the very first car he bought was a used car that he was using to, drive around college campus and go back and forth from home. It was kind of a beater. And one day the car overheated, which happens. It doesn't happen as much now as it used to, but it can still happen. And he wasn't thinking, even though he's a chemistry professor now, as a college student, he said, I just wasn't thinking. I knew the engine block would be hot, but he reached in there to open up the radiator. We're going to put some water in it, and the cap was really, really hot. And he grabbed it and, of course, burned his hand really badly, because you grab it and you let go really fast, but just like if you grab something on the stove, sometimes you can't let go fast enough, that heat exchange. So you can be in contact to have thermal contact, but you don't have to be. And of course, if you get the radiator cap off, then you've got the steam coming out. And steam is going to have more or less energy than water. It's going to have more because now it's got that translational piece to apply. So thermal contact, in this room right now, every object in this room is in contact with every other object in terms of thermal contact. So if I brought in a fan and started blowing the air in the fan, the whole room would eventually cool off. That's what our air conditioners are supposed to do, right? Obviously the air conditioner in my room works pretty good most days. So the thermal contact is not the same as physical contact. Anytime you can exchange heat energy, whatever heat energy is, then you get thermal contact. So there's our thermal contact piece. So what is heat energy? Just a few more words and we'll take a break. Heat energy is energy that flows due to temperature differences. And thermal equilibrium is when objects have the same temperature. So for example, if I have a block that's at 35 degrees Celsius and I put it beside a block in contact with a block that is 25 degrees Celsius, heat energy is going to run this way and this way until we end up at the same temperature. And what that temperature is depends on some other things, and we'll talk about it, but things like specific heat, phase, some things like that. So, but if we had the two blocks separated, 35 degrees, 25 degrees, as long as there was no insulator, heat would still flow back and forth. So let's talk about our last little bit here. Open, closed, isolated systems. You guys remember these from last year? Open system, closed system, isolated system. We're going to add a new piece of understanding on that. Open system meant what? Energy can come in, energy can go out. We don't conserve energy. Open system, matter can come in, heat can come in, or matter can go out, and heat can go out. So an open system allows particles in and out, and it allows heat energy in and out. So what do you think a closed system does? What would a closed system be? Closed system, heat can get in and out, but matter can't. If matter tries to flow in, it can't. If matter tries to flow out, it can't. So, matter is not allowed in or out. And an isolated system would be our Snuggie with a blankie. Our little system's got a Snuggie or a blankie. So, matter and heat inside, matter and heat outside, and this is a barrier. If you have a thermos, the thermos is the barrier. It doesn't allow heat in, it doesn't allow heat out, it doesn't let stuff in, it doesn't let stuff out. There's an isolation to the barrier. What do we assume in here a lot of times? That it's isolated? But here's the problem. There's no perfect isolate. You cannot perfectly isolate things. So even when I put my Diet Mountain Dew in my koozie, it helps minimize heat loss, right? Keeps it colder for longer, but it won't keep it cold forever. Even Yeti, who charges a lot for you to put those 4 letters on the side of a thermos. Yeti makes good products, but you know what I mean. Even those, they might keep it cold for days instead of hours, but at some point it's not going to stay cold. Or if it's warm like soup, it's still not going to stay warm forever. So there's no perfect insulator. You probably hear them called insulators as well. There's no perfect system on that. And heat energy will always flow from high temperature to low temperature. It would be awesome if I could take my soda out of the fridge and it would continue to get colder. I wouldn't be real happy with the removing heat from the soda and making the room hotter, though. Like, to give, you have to get. So one of the things that we have to give up here is heat energy always flows if we have a difference in temperature. Now, be careful about that, because equilibrium means same temperature. But if Elijah has family over to visit and somebody makes a wonderful, yummylicious apple pie, apple pie filling and apple pie crust may be at the same temperature. Which one's going to burn your little tongue if you're not careful? The filling. So they were both in the oven, right, at 350 or 400 degrees, whatever you're cooking at. Both the filling and the crust were at the same temperature. But same temperature doesn't mean I hold the same amount of energy as you do. Kind of like kindergartners and high schoolers. Kindergartners and high schoolers might be at the same energy. No, they're not at the same energy level, right? They might be at the same temperature, but the kindergartner will run all day. And the high schooler's like, okay, it's 2 o'clock, I need a nap. I had a nap at 10, I need one at 2, I'd like to have another one at 6. Right? Depending on how much schoolwork you have, naps are an important thing to do. But you know what I mean. So you got to be careful that thermal equilibrium doesn't necessarily mean contain same amount of energy. Because pie filling will burn your tongue and pie crust typically does not. Just like hot coffee will burn you much more often than a hot pastry for breakfast. Okay, so I'm going to stop and let that breathe, and then I'm going to let you work on whatever you need to work on for a little while. And then we may come back and take a few more notes later. We'll have to do ideal gas law tomorrow. Not tomorrow. We'll do ideal gas law on Friday.